So we have been discussing work, energy, power, etc. and some nuances of the various energies, for example the kinetic energy and how the kinetic energy is obtained. It's only because of the motion of a body or a particle, and we established in a way the energy work or work energy theorem, which we can discuss as the final kinetic energy minus the initial kinetic energy is equal to the work done. This is the formula that we obtained the other day in the other outing, in the other lecture. Now let us bear in mind, because there are many intricacies, there are many things about this, so that I am spending a lot of time on it. I am not going to rush through it because this is a very important topic. Here I have I am mentioning that what is done by a force or a displacement of a body, or a certain displacement of a body. And we found and we established, and we must bear in mind that the change in the kinetic energy is equal to work done. Now the second aspect of it is, what is a dot product of two vectors, the force and the displacement. So this is a scalar, and this also I am over here getting a scalar, and I am just trying to see what is the condition from this relation that we have, W is equal to F dot D is equal to Ft cos theta, when is the work equal to 0. From this relation we find readily that the work is equal to 0 under the condition that displacement is equal to 0. Okay, case that I discussed yesterday, a bicycle which is moving on a level road, and then a kind of a brake is applied, and the work done by the bicycle on the road is equal to 0 because there is no displacement associated with that. So in the first instance it is the displacement is equal to 0. In the second instance it could be the force which is equal to 0. Okay, there is no force applied, then there will be no work done. And the third case is when this also exists, but the cos theta is equal to 0, which means that theta is equal to plus minus 90 degrees. Now this is another aspect, and we will discuss that, a case of 0 work done, here in the case of a moon going round the earth in a circular orbit. Normally the orbit of a satellite, like planets going around the sun, that is elliptical, but the ellipticity is so small that the two foci of the ellipse, I'll tell you about that, they merge into one point and it becomes the center of the ellipse, and in that limiting case the ellipse becomes a circle. Okay, so I'll talk to you about that later. But looking into the theta, if it is in the first quadrant, then the cos of theta is positive. Here the cos of theta is negative. Okay, and here the cos of theta again is negative, and in this case the cos of theta becomes positive. Okay, so I have just taken two cases which are obvious, which are of value to us, in which in the first case the theta lies between 0 degrees and 90 degrees, in which case cos theta is positive, and therefore this turns out to be a positive value where F exists, D exists, theta also exists. So W is positive, the work done is positive. There is another case, if it is in this quadrant in between 90 degrees and 180 degrees as it appears to you, then the work done becomes equal to negative because cos theta has a negative value. Okay, now look here, I am taking example of the moon going round the earth. Of course, we have to calculate as to what is between the mass of the earth and the mass of the moon and the radius of this moon's path, etc. And we can calculate what is known as the force of gravity. The force of gravity of the earth on the moon, which is also equal to the force of the moon on the earth according to third law, okay, which is a bit strange because sometimes there is difficulty in application of the third law. Because action and reaction pairs take place, a pair of forces, they take place on two different bodies, and you have to be very careful about that. So here in this case, I have the force of gravity applied on this mass, and this force of gravity, which is the force on the body moon by the body called earth. And you can see that the velocity of the moon, it makes an angle of 90 degrees with the direction towards the center in the radial direction. This is the radial direction, which provides for FGR, provides for the mv square upon r, which is the centripetal force. But you can see that here the movement of the body, the displacement of the body moon in its orbit, okay, and the force, they make an angle of 90 degrees. So therefore the work done by the gravity on this system is going to be equal to 0. Okay, so the force is there and the body is moving, but what happens is that in case of cos theta being equal to 0 or theta being equal to plus minus 90 degrees, whatever, that's your choice here, you have to check what angle will be there, etc., etc. And before, another aspect I would like to tell you about what is the dimensions of work done or energy. Look here, ml t minus 2, this is the dimension of force. L t minus 2 is the dimension of acceleration. Multiplied by m, I get the force. Force multiplied by L, okay, so this d over here, this gives ml square t minus 2. The unit, which is a Newton into a meter. A Newton into a meter, that is described as joules. Joules was a scientist, very important English scientist, okay, in whose name we have taken the unit in the SI system or system international, and this joules happens to be equal to 10 to the power of 7 ergs. Okay, ergs is the unit in the CGS system. Centimeter gram second system, the unit of work is this. I am showing over here because the unit of force, which is Newton, is equal to 10 to the power of 5 dynes. You have to work it out, okay, by the same formula mlt minus 2, and you find that this is 10 to the power of 5 dynes, and 1 meter which exists here is equal to 100 centimeters, so it turns out to be 10 to the power of 7 dynes. I'm sorry, 10 to the power of 7 ergs. There are other units in the books, they describe the other units of work done or energy. In the heat we use calories. In the electrical concepts we use electron volts, and also for calculating the expenditure of energy in the household we have kilowatt hours. So all these things are there, and all books they give that. You must be able to be conversant, convert one into the other. Now I'm going to give an example to you of a situation, and the situation is very simple. The situation that I'm going to do is, and I'll make the diagram shortly, is the drop of water falling on the earth. And remember, I calculated for you the velocity of the drop on reaching the earth. If there were no resistive forces of air, etc., then the drop from a 2 kilometer height, please remember, I'll recalculate just now, it will turn out to be, if we use the formula, v square is equal to u square plus 2gh. So from 2 kilometers, if the drop drops, maybe I take the mass of the drop as 1 gram. So in that case, the velocity is, what is obtained is 200 meters per second. But normally when it is raining, then the velocity of drops is much smaller than that, because although a 2 kilometer is a small height, and between 2 kilometers and the surface of the earth, we can consider the value of g, the gravitational field, to be constant, and can take it as 10 meter per second square in our estimation calculation. But what happens is, we'll find that experimentally it is found that when it reaches the ground, then this drop has a velocity of 50 meters per second. So what is going to happen? I can find out the total work done by gravity on the fall of the drop, while we don't know what are the velocities of the drop in between, from 2 kilometer height to a 0 meter height. We find that the difference of the kinetic energy, okay, and the work done by the gravity, it happens to be much more than the difference of the two kinetic energies. If I take this initial kinetic energy is equal to 0 and calculate the kinetic energy as half m into v square, where the velocity has been taken as 50 meters per second square, then this turns out to be, as I will calculate, 1.25 joules. Okay. The work done by the gravity, if we calculate, that turns out to be 20 joules. For this small 10 to the power of minus 3 kilograms drop of water, the work done by gravity is 20 kilometers. Then, now there are two things. One is the work done by the gravity, and the other is the work done by the resistive forces, okay, of the drag of the atmosphere or drag of the air through which it goes. And you'll find that that turns out to be so what is the work done by the force of drag or resistive force which the earth is the air is applying on the drop while the drop is falling, okay, that will turn out to be 20 less, 1.25, whatever it is, the difference of the two kinetic energies minus the work done by the earth, and that is 20. So 1.25 minus 20 will turn out to be minus 18.75. So the work done by the air on it, this system where we have scant knowledge, little knowledge of what is happening, when is the terminal velocity achieved, okay, etc. Terminal velocity one day we are going to discuss, and then you will find, you will be surprised that what Mr. Aristotle used to say was also correct in a practical situation like that. So the interesting problem that I introduced to you is, now my drop here of mass 1 gram, which is 10 to the power of minus 3 kilograms, is the height of 2 kilometers, which is 2 into 10 to the power of 3 meters. It is released by the clouds, and it drops naturally towards the earth, and it obtains a velocity of 50 meters per second on reaching this ground zero level. Okay. In between, what is happening is, since the beginning, the gravitational force is acting, and over a span of this 2 kilometers, which is a very short height, as compared to 6,400 kilometers, 6,400 kilometers of the radius of the earth, okay, kilometers. So this 1 kilometer is very, very small, okay,
Kilometer.
negligibly small.
Kilometer.
Hmm?
Kilometer.
Oh, this is kilometers, okay, not kg as I wrote there, I have been corrected. So this is 50 meters per second, the velocity which is obtained over here, calculated over here. Now this is the problem, and we will try to see as to what will happen. So first of all, if the resistance of the air, which may result in what is called terminal velocity, which I said that I will talk to you about that terminal velocity later, which depends upon the mass of the drop. If the resistive force is equal to 0, which means if there is vacuum between the height of 2 kilometers and the ground level, if there is a vacuum, there is nothing else, no air, no nothing, okay, something called nothing, okay, vacuum is there, then we find from this relation v square is equal to u square plus 2gh. I have used here from the kinematical relationship, and writing the values 2 into 10 for g and 2 into 10 to the power of 3, then we calculate the value of v as 2 into 10 raised to the power of 2 meters per second, which is 200 meters per second. So from our theoretical calculation, the drop should come here with a velocity of 200 meters per second, which is very high velocity, okay, even if it is sputtering, okay. Then now see, what we can do is, we can calculate the final kinetic energy minus the initial kinetic energy, okay, which we'll take as half, because the initial kinetic energy is equal to 0. So the final kinetic energy will be determined by the velocity that we have, 50 meters per second. So half into 10 to the power of minus 3, which is the mass of the rock, into 50 square, and that turns out to be 1.25 joules. Okay, so this is basically determined. There is nothing about the height, it is only about the difference of the kinetic energies at the two levels, 2 kilometer over here at the top, and at h is equal to 0 in the ground level. So this is 1.25 joules. Now let us see what is the work done by gravity, by the gravitational field of earth. So this I can say that the force is mg, and the difference and the height difference is equal to h. So I can say, I calculate it out and it turns out to be equal to 20 joules. 20 joules. No, it is not 20 joules. It is plus 20 joules. I must write it as plus 20 joules. So the work done by gravitation on the drop in its travel from a height 2 kilometers down to the ground level is plus 20 joules. Why? Because the gravitational force and the direction in which the drop moves, they are both in the same direction, and therefore I can calculate it as 20 joules. Now, work energy theorem says that the change in the kinetic energy is obtained by the work done. W delta K is equal to work done by gravity plus work done by the resistive forces of the air. And when I work it out, then I get the work by the resistive forces, air, etc., whatever is there, okay, is, we don't know about it. But now we can calculate. I have the calculation here, another this calculation plus this calculation. They are okay. So 1.25 minus 20 turns out to be equal to minus 18.75. As I told you, minus 18.75. So the work done by the resistive forces on this drop is a negative work done, and it is equal to much minus 18.75 joules. So this is how we go for negative and positive work done. And I told you before that there is zero work done when it is equal to, the theta is equal to 0, 90 degrees. Okay. So far as we have discussed about a constant force, but now the force may vary over a distance, and then we are trying to calculate the work done by a variable force using the nuances of integration, and then if I have very thin strip of delta x and fx, then this thing will give us the area, that delta A is equal to fx into dx. Okay, fx into dx. Of course, the area the total area, if I take all these strips from here to here, from xi to xf, I will get the work done as a summation xi to xf, fx into delta x, small strips of delta x. Or using the nuances of integral calculus, if delta x tends to 0, then I can write it as xi to, between the limits, initial and the final value of x, I can write it as fx dx. Of course, if fx is constant over the total distance in which things happen, as is normally explained, we find that fx is not a function of x. It doesn't depend upon it, it is independent of it, it doesn't vary. So non-variable force, what we find is, in a similar fashion, I find that the total area is equal to fx multiplied by the final value of x minus xf minus xi. Okay. Now the next item that I take up is work energy theorem for a variable force confined to one dimension. So we are going to derive and explain to you a work energy theorem for a variable force. Before we did it for a constant force, and we obtained the same kind of relation which we are going to derive now. So what we do is that at any instant of time I differentiate and get a derivative of the kinetic energy and substitute for the kinetic energy the mass into the velocity square divided by 2, so half mv square, which if I work out here, then it will be 2v here, so 2 and 2 cancel, and I group this m dv dt here and v over here, so this becomes equal to the force, so I can write it as force multiplied by the velocity, which velocity of course can be expressed in dx dt. So if now I have dk dt is equal to f dx dt, dt can cancel out and we can write dk by the nuances of calculus, okay, that dk is equal to f into dx. So from a limit of initial kinetic energy to a final kinetic energy, if I integrate it, then on this side I will integrate it for x is equal to xi to x is equal to xf, and so I obtained here kf minus ki is equal to this quantity, which I can write as w because it's the definition of the work done. Okay. So this presents for us the work energy theorem of variable force. Okay. So you see that this that we obtain over here is an integral form of second law, Newton's second law, F is equal to ma. You know that at any instant of time, the Newton's second law relates acceleration and the force at that point. The work energy theorem involves an integral over an interval of time. Given interval of time, the integral is carried out and we are able to obtain this f k final minus k kinetic is equal to w. Now the next thing that we have arrived at this, and I have already defined for you what is the kinetic energy, what is the potential energy. I've obtained the expression for kinetic energy and potential energy not only in a constant force, for example in the gravitational field of Earth, or gravitation under the when small g works, also in the case of a spring where the position was done, there also I found that energy, potential energy associated with the spring is equal to half kx square, where F is equal to kx, where that small k was for the force constant of the spring. Okay. So we carry from here. Again, I desire you and I urge you to reread these things from any books that you are following. We have a very nice set of books in India and from our NCERT, National Council of Educational Research and Training. They have a long experience of writing these texts, and they are really very beautiful texts with the omissions and commissions. So we must put in the omissions. We should see as to why the commissions are there, and I will talk more about that and then introduce power. Okay, it will take us a couple of lectures, so bear with me because this is topic, I told you, this is a very dangerous topic because it is very simple, and simple things are always dangerous. I have found in my life experience. So thank you very much. See you again.